All right, chemistry, let's take a look at your video lecture for chapter 11, sections 1 and 2. We are going to be combining both of these sections, running through them together. So at the end of section 1, I want you to be able to state the law of combining volumes. We're talking about gas here, and so we're talking about volumes. And combining volumes is going to be the foundation for us being able to go back to using stoichiometry skills using gases. So we have to be able to combine volumes to start, right? And we'll build from there. Then I want you to state Avogadro's law and explain its significance. Again, we're building back to being able to do stoichiometric calculations, but with gases. Then define standard molar volume of a gas and use it to calculate gas masses and volumes. Lastly, use standard molar volume to calculate the molar mass of a gas. And I hope you see that once you have the mass of something and the molar mass of something, you can convert into moles of that thing. And once you are in moles of that particular substance, now you can do stoichiometric calculations. So let's start by being able to measure and compare volumes and combine them. In the early 1800s, French chemist Joseph Gay-Lussac observed that 2 liters of hydrogen can react with 1 liter of oxygen to form 2 liters of water vapor. Right? According to this equation right here, hydrogen gas reacting with oxygen gas forms water vapor. We get 2 liters of H2, what we now know to be H2, but he did not know it was H2. In fact, he thought it was just H. Right? There's 2 liters of hydrogen, 1 liter of oxygen, and 2 liters of water vapor. This reaction shows a simple 2 to 1 to 2 ratio in the volumes of reactants and products. Again, in volumes, right? Not necessarily how much is there per se, but we're measuring volumes here. Now, this same ratio applies to any volume proportions. For example, if we're only looking at milliliters, it would be 2 milliliters to 1 milliliter to 2 milliliters, or 600 liters to 300 liters to 600 liters. Again, it's always a 2 to 1 to 2 ratio, regardless of the scale at which you're operating. So the same simple and definite volume proportions, right, they're defined, a 2 to 1 to 2, can be observed in other gas reactions. For example, when you combine hydrogen gas with chlorine gas to form hydrogen chloride gas, it's a 1 to 1 to 2 ratio. So as we observe this, we get Gay-Lussac's law of combining volumes of gases. And so in chapter 10, we talked about Gay-Lussac's law. And Gay-Lussac's law related pressure and temperature of a gas. Please do not make the mistake of thinking Gay-Lussac's law of combining volumes is the same as Gay-Lussac's gas law from chapter 10. Be on the lookout for that term, combining volumes. But Gay-Lussac's law of combining volumes of gases states that at constant temperature and pressure, okay, so we have to have certain things constant, the volumes of gaseous reactants and products can be expressed as ratios of small whole numbers.
In the early 1800s, Joseph Gay-Lussac studied the relationship between the volumes of gases involved in chemical reactions. He found that 1 volume of hydrogen gas reacts with 1 volume of chlorine gas to form 2 volumes of hydrogen chloride gas. No matter what volume of gases he used, the ratio of hydrogen and chlorine remained the same.
So we can combine volumes, and we can almost see in the chemical equation that there is a ratio of volumes of either reactant to reactant or reactant to product or even product to product. There's going to be a small whole number ratio that should remind you, or hopefully, if I remind you, that should remind you of the small whole number ratios of coefficients in a balanced chemical equation, because that's where we're headed. Next step, Avogadro's law, right? You've already heard the name Avogadro. He has that special number, 6.022 times 10 to the 23rd, right? That defines how many particles are in a mole of a substance. It's that same guy. In 1811, Amedeo Avogadro explained Gay-Lussac's law of combining volumes of gases without violating Dalton's idea of indivisible atoms. Okay, so this is not Avogadro doing completely different work, not coming up with the same thing, but explaining why Gay-Lussac's law of combining volumes is the case. This is an idea to explain why something is the way it is. Now, what was so nifty about what Avogadro did is that at the time, Dalton's atomic theory was the leading idea, definition of what an atom, the indivisible things, are. And so he was able to explain why Joseph Gay-Lussac was observing this law of combining volumes while maintaining the idea of the indivisible atom. Avogadro reasoned that instead of always being in monatomic form, right, one atom, when they combine to form products, gas molecules can contain more than one atom. This was a brand new thing. He also stated an idea known today as Avogadro's law. The law states that equal volumes of gases at the same temperature and pressure, right? It has to be the same temperature and pressure. That's why STP, standard temperature and pressure, is so useful for us. That at the same temperature and pressure, they contain equal numbers of molecules.
If we filled balloons with the same volume of different gases, they would all contain equal numbers of molecules. But if we weighed each balloon, we would find that they did not have the same mass. We have the same number of molecules in each balloon, but the mass of the molecules in one balloon differs from the mass of the molecules in the other balloon. This is why in air, a balloon filled with hydrogen or helium rises, and a balloon filled with carbon dioxide sinks.
So Avogadro's law also indicates that gas volume is directly proportional. Remember, directly proportional, when one changes, the other thing changes in the same way, is directly proportional to the amount of gas at a given temperature and pressure. Again, we have to be constant in terms of temperature and pressure. The equation for this relationship is shown below, where V is the volume, K is a constant, and N is the amount of moles of the gas. Right? That's going to come into play quite a bit this chapter. N represents the number of moles of that gas. So Avogadro's law applies to the combining volumes in gas reactions and applied that to the combining volumes in gas reactions, and it helped him to deduce that chemical formulas in reactions. Dalton had guessed that the formula for water was HO, right? One hydrogen and one oxygen, which we now know is not the case. But Avogadro's reasoning established that water must contain twice as many hydrogen atoms as oxygen atoms because the volume ratios in which the gas is combined. 2 liters of hydrogen for every 1 liter of oxygen, right? So instead of combining at a 1-to-1 ratio like Dalton thought, they must combine at a 2-to-1 ratio because it takes twice the volume of hydrogen to react with 1 liter of oxygen. So, given Avogadro's law, the simplest possible chemical formula for a water molecule was indicated by 2 hydrogen atoms and 1 oxygen atom, which we now know to be the case, H2O. But in order to make sure that the law of conservation of mass was satisfied, we had to now bring into play these coefficients to balance the chemical equations. Avogadro's idea that some gases, such as hydrogen and oxygen, must be diatomic, right, was thus consistent with Avogadro's law and a chemical formula for water of H2O. Now we need to move on to the standard molar volume of a gas, right? Again, we're taking steps going from this idea, the idea of a gas, and how we can describe things like pressure and volume. Specifically volume, we can take volume and then convert that into a number of moles. And then, like we learned in chapter 9, we can take that molar amount, the number of moles, and then we can convert that into almost anything we want. We can convert that into the mass, we can convert that into number of particles, we can convert that, what else do we have? What we have now in liters, volume. We can go from volume to moles. So recall that 1 mole of a substance contains a number of particles equal to Avogadro's constant. Remember, that's 6.022 times 10 to the 23rd. For example, 1 mole of oxygen, which is O2, contains 6.022 times 10 to the 23rd diatomic molecules. Because remember, we just learned that oxygen's diatomic, O2. So according to Avogadro's law, 1 mole of any gas will occupy the same volume as 1 mole of any other gas at the same conditions, despite the mass differences. Refer back to the little video from Robot Lady if you want another visual representation of that. So the volume occupied by 1 mole of gas at STP, remember standard temperature and pressure, okay, that's 0 degrees Celsius and 1 atmosphere of pressure, is known as the standard molar volume of a gas, which is 24.41410 liters. But in this class, we're going to round that down to 22.4 just because it's a little bit more convenient. So at standard temperature and pressure, 1 mole of any gas is going to take up 22.4 liters. So knowing the volume of gas, you can use that conversion factor of 1 mole over 22.4 liters to find the moles, and therefore by extension, the mass, of a given volume of gas at STP, as long as it is at STP. For example, at STP, 5 liters of gas can be converted into moles of that gas using the conversion factor of 1 mole over 22.4 liters. Notice that the liters will cancel out, and mole will be the only unit left there in that first example. You can also use the molar volume of gas to find the volume at STP of a known number of moles or a known mass of a gas. So instead of starting with liters of a gas like we do in that first example, we can start with moles of that gas, use this same conversion factor, just invert it so that moles cancel, and now we're left with liters. We can calculate the volume of that amount of gas. So let's try this. Simple problem for A. What volume does 0.0685 moles of gas occupy at STP? And then, going the other way, what quantity of gas in moles is contained in 2.21 liters at STP? So, for the first one, what do we know? We know that we have 0.0865 moles of gas at STP. We want to find the volume in liters of that gas. So we're going to use the conversion factor that's going to allow us to cancel out moles, right? Because moles is the unit that was given to us. Cancel out of moles and go into liters. So that's 22.4 liters over 1 mole. Simply plugging this into your calculator will give you 1.53 liters of gas. Now we can go the other direction as well. We can be given a volume. We can be given liters. As long as it's at STP, we can use this conversion factor. 2.21 liters of gas at STP, we want to convert out of volume and into moles. So again, we'll use the same conversion factor, just invert it so that the liters will cancel and mole will be the only unit left. And so once we divide these two values out, like this math indicates, we come up with 0.0987 moles of gas.